Hello everyone, my name is Peng, a graduate student from the University of Notre Dame. Today I will introduce our recent work, PHG-Net, Persistent Homology Guided Medical Image Classification. This is the overall motivation of our method. First, the CNN or transformer backbone tends to neglect some key global or robust anatomical structures. Second, the medical images commonly contains like tissues, organs, or lesions as connected components with specific patterns. Third, the persistent homology can incorporate the topological information, for example, connect components, loops, or voice into the deep learning network. Our task is medical image classification. To be specific, we focus on classifying the skin lesion type, the prostate cancer degree, and determine whether the mammographic classification is benign or malignant. The tool we used to extract the image topological features is cubical persistent homology. Given an input image I and a series of threshold values T0, T1, Ti, we threshold the image I as a sublevel image STI equals to the pixels whose intensity value is less than or equal to Ti, and the sequence of STI forms the filtration. The homology groups are induced as HST0, HST1, HSTI, and which records the topological features of STI. And the topo Ti Tj is recorded and plotted as a 2D point with Ti on the x-axis and Tj on the y-axis, which is shown in figure C, and Tj minus T1 denotes the lifespan of the topological structure. This is the overall structure of our proposed framework. It has two branches. The top branch is a common CNN or transformer network, which hierarchically extracts the vision features, and the bottom branch is our proposed persistent diagram encoder. Specifically, we treat the persistent diagram as a point cloud and design persistent diagram encoder to encode the persistent diagram into a one-dimensional feature vector. Then we use a fully connected block to incorporate the one-dimensional topological feature vector into the features of the CNN or transformer backbone. And the loss function is a summation of the vision classification loss and the topological classification loss. This is the overall structure of our persistent diagram encoder. We treat the persistent diagram as a point cloud and use the point net to encode the persistent diagram into a one-dimensional topological feature vector. In figure B, we show the residual block that is incorporated with the topological feature. This is the experimental results on 3 publicly available datasets. We can observe it from the table that on the ISIC skin lesion, prostate cancer, and the CBIS DDSM mammography image, our proposed PHG module is able to boost performance by a large margin. Also, to demonstrate the significance of our performance improvement, we do the paired t-test, and the p-value is less than 0.005, demonstrate that the improvement against previous methods is significant. This is the ablation study. We tested our PHG module on 2 backbones. One is CNN, that is the SE-Net 154. Another one is a swing transformer. We compare our persistent diagram encoder with the Pursley and PLA method. We also compare our PHG module with concatenation and knowledge distillation method. From this ablation study table, we can see that our proposed persistent diagram encoder outperforms the Pursley and PLA, and our proposed PHG module also performs better than the pure concatenation and knowledge distillation method. We tested the computation complexity of our method. Given the input image resolution of 224 and the persistent diagram length of 300, the performance between sharing and not sharing parameters among different persistent homology groups are similar. The additional number of parameters flow posts introduced by our method is very limited. This is the validation loss of different type of methods incorporating persistent homology information. As we can see from these figures, our proposed PHG-Net has lower validation loss compared to other methods. We show some qualitative examples of our proposed method versus other methods. This figure shows the heat map generated by different methods. The columns A to E denotes the input image, PLA, Pursley, knowledge distillation, and our PHG-Net respectively. From this figure, we can see that our proposed method can help the backbone network focus the attention on specific areas of interest. In summary, our contributions are in three aspects. First, we proposed to incorporate the topological feature into the CNN or transformer backbone network. Second, we proposed to treat the persistent diagram as a point cloud and use the point net to extract topological features. Third, we demonstrate the effectiveness and the computation efficiency of our proposed method on the ISIC 2017 prostate cancer and CBISDDSM classification datasets. That's all of it. Thank you for listening.